Today is Monday, June 6, 2022. It is day 323 of data science, and today all that I will be doing is basically rewriting this whole thing, but like in nicer terms, kind of like this. Although this is not neat handwriting, but like basically summing all of this up on the right to something like the left. And so day 321, right, I think, is the day where I performed a hypothesis. And so the question was, do we have convincing evidence that there is a difference between the true mean difference in distance traveled by gummy bears? So that was a whole hypothesis test. It turns out that we don't, because the p-value was greater than alpha, or the significance level. So because of that, we failed to reject the original hypotheses and did not have convincing evidence for the alternative hypotheses, which is that there is a difference. And so that's the conclusion that we reached. And so today I'll basically, again, I'll just be writing it just like, I'll be setting it up in my doc like I did for the confidence interval that I did on, I don't even know what day. So yeah, so I guess that I'll be, maybe I'll take a screenshot. If I go here, whoops, no. Export image. Wait, let me zoom in. Alright, so export image. Have that there, and then I'll like pull it up just in case. Alright, open file. And then, okay, just have that there, and then I'll go over here to home and then open up a new file. Word. So, okay. So again, it's a hypothesis test, and so we're going to use Phantom. So P stands for parameter, H stands for hypotheses, A stands for assumptions or conditions, N stands for name of procedure, T stands for the t-test, O stands for obtain p-value, and M stands for make conclusion. So let's write that all down over here. So we'll start by, this is basically like the shortened video of the last video. This is, I think, log 5. So I think this is like the shortened version of log 4, because log 4, I I explained a lot of things. Anyway, so I don't like the way that I write. Let's do Phantom. Okay, so Phantom. So I'll do P. So P stands for the parameter, which in this case is mu diff. And that is the true mean difference Oh, I hate my handwriting right now. In distance traveled by gummy bear. What? In distance traveled by gummy bears. Right. And then A stands for the assumptions. So the first one is random, second one is 10% rule, and 3 is normality. 1 second. Alright, so the first condition, again, it's that the sample is random. So I know that it's random because I took a simple random sample of 30 gummy bears, or at least the mean difference column is generated from a simple random sample of 30 gummy bears. So that condition is checked. Second one is independence, so that's the 10% rule, or you could just think of it as independence, and this is when the sample size is less than or equal to 10% of the population. So we know that n is 30 because that's the sample size, right? And we know that that is reasonably less than 10% of all gummy bears because that's the population. We don't know the actual size of all gummy bears, so we just say that this is reasonably true, but we can't literally prove it, but so we say it's reasonably true, and then we just say, it's check done. So make sure you say reasonably true. All right, and then lastly, what's again? Okay, normality. I was like, what is it again? Normality. This is when n for means is greater than or equal to 30. So we already know again, 30 is greater than and actually equal to 30. So this condition is checked, and therefore we can go and proceed with the what the heck am I saying? Significance test. If by any chance there's a condition that is not met, at least College Board wants you to continue to proceed with the test, so you just say proceed with caution. You specify which condition is not met, and then you continue to proceed with caution. Okay. And then N is the name of the procedure, so that's a one sample T test for mu diff, right? Or you could say mean difference or average difference, whatever you prefer. T is, our actual t-test. So our t is equal to a certain formula. Where's my stuff? Okay. T, right, is equal to, I just know that I have s of x over the square root of n, and then I have x bar minus mu. So that specifically is going to be equal to, I know that this is 48 something. We get that from our data here. If I go back to day 321, I know that my standard hold on, I'm trying to look for it. Oh no, this is to calculate the t-test. Where's my stuff? Where is it? Okay, it's over here, yeah. So I know that this is going to end up being negative 0.9313. I'm rounding it to 4 decimal places. I'm getting this from this selection right here. Basically, this function I wrote, what am I saying? I can't even speak. This function, I wrote it so that it gives me the formula with the numbers plugged in. So yeah, basically. So I'm going to do minus 0. So 0 is mu. This number, oh my god, I forgot the hypotheses. Okay, let me just do something real quick. Cannot believe I forgot to find hypotheses. How am I supposed to move these? What? Okay. Move this here. Move this here. All right. So for the hypotheses real quick, because I tend to forget that one. HO is, your original hypotheses, and then you have HA, which is your alternative hypotheses. So original hypotheses is basically what is known. It's kind of like the safeguard until proven, like, not that it's not true, but you find evidence for another alternative hypotheses. So in this case, our mu diff, so our average difference, is equal to 0, and then our alternative hypotheses is that it's not equal to 0. So what does this mean? This means that there is no difference. This means that there is a difference in the average mean difference in distance traveled by gummy bears. I know, it's a mouthful. So now back to the point that I was trying to make. Whatever number is here is the same number that is here for mu, right? Because this is the alternative hypotheses that you're trying to test. And so you're trying to find the test statistic given that alternative hypotheses. And when we find that value, when we find that t value, we can see if that t value is significant enough by comparing it to our significant level, to our alpha, which is our significant, oh my god, sorry. Significance level. Yeah, anyway. I'll get to that in a point. In a point, really? Oh my god, I cannot speak today. I'll get to that in a second. Like, what is going on? Okay, and then the standard deviation is 48.8605 divided by the square root of 30. And then when you put those answers in, you get t is equal to what was it? 0.1044. Now it is negative, but we take the absolute value of it and we also take the negative value. So to draw a picture, I'll show you what that looks like. So let me see. So that's not a straight line. Okay. Oops. If I could just draw one nice normal distribution, but it's really not happening right now. Oh, that was kind of good, but this is really upsetting right now. No, I'm playing. Yeah, we're gonna, actually I cannot bring myself to go with that. It's so ugly. Okay, that's fine. So basically this is a normal distribution. How do we know that? Okay, basically let me rephrase this. The graph of the data looks like this. How do we know? Because we checked for normality. So the sample size is greater than or equal to 30, and therefore, okay, it's a normal distribution, because that's like the law of large counts, that the more data you have, ultimately they all end up looking like a normal distribution. So this is a normal distribution, right, with a mean of negative 0.9313 and a standard deviation of 48.8605. All right, so the mean ends up always being in the middle, right, because it's normally distributed, and that means that it's symmetrical, meaning that on the left and right side they're basically the same. So all right, and so the t-test or the t-statistic is this number, right? So that number ends up being somewhere, what is 0.1, so we'll say 0.1044 is here, negative actually, and then 0.1044 positive is over here. And so what I just did, this section from there to there is the rejection region for HO. So this is the rejection region for HO, and this is the rejection region for HO. And basically, we're trying to find, the O part is to obtain the p-value. And so what we do is, we basically try to find, we use t.cdf, but there's different ways to do this. We could do a t-test, t.cdf in your calculator. I use a Python function. But the idea is that we're trying to find the area, like the area right here under this curve, right? And the area under this curve, and add them together, or just take 1 and multiply by 2. And that's going to be the probability, right, of rejecting HO. So in order to find that area, right, we want to, there's a few different ways. You could do, well, The first one is a table. Do not recommend. Literally nightmare. Google it if you want. I don't even want to get into it. Table, then you have, if you have a TI-84, you could do t.cdf. If you have a TI-84, you could do a t-test. With t.cdf, you have to multiply by 2 if you're doing a two-tailed test. With a t-test, you don't have to multiply by 2. You know it's a two-tailed test if your alternative hypothesis has a not equal sign. So because it has a not equal sign, we're taking both sides. If it was a right-tailed test, we would only take the probability of this. If it was a left-tailed test, we would only take the probability of that. But because it's a two-tailed test, we're taking both tails, right? Right tail, left tail, etc. So, and then the way that I like is technology. So I used Python. Well, this is technology too, but more advanced technology. I used Python to basically make a function that calculates a t-stat for me. And so I used one function specifically, actually. I made my function, it's called a one sample t-test for mean given only t-stat, n, and mu. And then I just did, well, you don't know about degree freedom yet. Well, anyway, the way, I'll show you actually how to do the TCDF real quick. So if you're on your calculator, you would do basically TCDF. You would find it in your calculator. You can Google that part. I forgot how to get there. And then it's going to ask you TCDF. It's going to ask you for lower bound, upper bound, and then degree of freedom. And so lower bound is basically where you're starting. Upper bound, it's like the interval. So you know in math class when they have a graph and they're asking you, okay, what's the domain of this graph? And then you give like an interval. Well, it starts over here like at -3 and it ends over here at 3. And so the graph runs from -3 to 3. Same thing. We're just saying, we're just telling the calculator what interval to calculate the probability. So if from here, right, but we know that a normal distribution goes on into -infinity, but it ends up over here at this t-stat. So what does that look like? Well, a calculator doesn't have a -infinity symbol, so in order to do that, we use like an arbitrary, really? So I cannot pronounce that word. Anyway, a number that kind of represents that. So I do -E99, and then my upper bound would be, this right here, right where it stops, because that's the probability that I want to calculate. So let me do this real quick. So it's going to end up looking like -E or -1E99. Upper bound would be my -0.1044. And then my degree of freedom, the equation for that is n-1. Always, unless you're doing an LSRL. But n-1, right, so 30 minus 1, 29. So 29. And then you would just click enter, and then it would give you like 1.0824, and that's your answer. So that's going to be your p-value. That's the probability of this, or like the area of the red above, right? Anything else I wanted to say? Let me see. Oh, and the reason we started by using the negative instead of the positive is because my t-stat was like negative originally. So that means I would just, do the negative and then multiply it by 2. Oh, excuse me, I forgot. Multiply this by 2, and then you get that p-value. Alright, and then the other way that I like to do it is my own function over here. It's basically, it's just asking you, like, let me run it again. So I just call the function and then put my stats here. So I have n, 30, 0 for my mu, and the t-stat, I already set the variable up here somewhere. Hold on. Let me see, where is it? Oh, over here. So my t-stat, I'm going to have to run everything from the beginning. Alright. Oh, and I have to upload it. That's great. Yeah, because I'm doing this for my data. I'm not putting in the numbers manually. I'm having Python calculate them. Where is my stuff? Gummy Bear Project. Was it this? I think so, yeah. Okay, so go back up. Run that. And everything should be fine. Alright, so If it's a two-tailed hypothesis, if it's a two-tailed test, your alternative hypotheses will have a not equal sign. Is this a two-tailed test? And then I'm going to say yes, because my alternative hypothesis has a do not equal sign. And then it's going to give me my t-test. Note that I put in the 30 manually. I put the 0 in for mu, right, over here. And then t, I just put the variable t-stat, which I defined over here with my t-stat function. And my t-stat function is just, I just did one sample t-test for mean. I put the sample size, the x bar, which is x, and then s of x, which is the standard deviation, and then the mu. So that would be like n, x diff, which I defined somewhere up over here. I just took, I just used the mean function, and then I got the mean of that column, set it equal to x diff, whatever. I did this in day 321, yeah, just go look. Anyway, whole point is, put the t-stat in there, and then it gave me that. And so essentially, if I say yes, that it's a two-sided test, and it takes the p-value and multiplies that area by 2, it takes that area, multiplies it by 2, and sets that equal to the p-value. If it's no, then, it's just, if it's less than 0, the p-value is 1 minus the area. If it's greater than 0, the p-value is just the area, right? Actually, now that I think of it, isn't this supposed to be the opposite? If it's t is less than 0, 1 minus the area. But it's CDF. And CDF calculates the probability below or left. So why would I do 1 minus the area? That would give me the probability of above. I think this is wrong. This over here, these conditions. Interesting. This is definitely right, but then I don't know why this is like this right now. Anyway, not a problem of today. Okay, and so that's my t-test, and not my t-test, my p-value. So what do I do with this p-value? I make my conclusion. So at this point, this is really not even like neat, like at all. I have to like rewrite this again. I'll do it later. So my main conclusion is because my p-value of 1.824 is greater than my alpha level, which is 0.05. How did we come up with that? 95% confidence level gives you a 0.05 alpha level, because alpha is actually equal to 1 minus the confidence level, and so 1 minus 0.95 is equal to 0.05. Hopefully, right? Hold on. Let me make sure. Yeah. I'm literally losing my voice. Okay, so because blah blah blah, the p-value is greater than alpha, we fail to reject HO and do not have convincing evidence for for a difference, or evidence that there is a difference in the average difference average difference in distance that gummy bears traveled. This is so slappy. Alright, and that's the whole idea. So I'm gonna go ahead and rewrite that because this looks so ugly. So I think what I'll do is I'll just take this part because this is fine. Maybe take a little bit of that bottom part. Are you kidding me right now? Why does it do this? It's not moving. You know what? It's okay. It's not like I need this stuff over here. Let me just erase it. And I'll just write it from the beginning. Alright, alright, so T is equal to mu minus, ooh, I forgot something. It's actually mu, the mean difference minus the mu difference over the excess difference divided by the n difference, and that's equal to 48.8605 divided by the square root of 30 and then I'll do the mu difference, which was what, negative 0.9 3 1 3 minus 0, and then we say that t is equal to 0.1044 was negative, and then O is obtained p-value, so I do t.cdf, and I do negative 1e99, I do negative 0.1044, lower bound, upper bound, and then degree of freedom is 29, and then I do, I multiply this by 2, and I get 1.0824, and then I make my conclusion. So because 1.0824 is greater than 0.05, we fail to reject HO and do not have convincing evidence for, or not for, that there is a difference in the mean or the average difference, in distance traveled by gummy bears. And then close that. What? I never asked for the ruler. Alright, and then I'm gonna go down here and erase all of that. Alright, and then I'm gonna go over here. And I'll erase this red here. And then we'll go here, export image, high resolution, export, and then open it up over here. And then I'll do Control S, and I'll save it as hypotheses test here. And then I'll go to my doc, and then I'll do insert image, upload from computer, and I'm gonna try to find it. Hypotheses test. Ugh, it's so ugly. Okay, first of all, I promise that my handwriting is literally so much better in real life. I do not actually write like this. I just don't know why it's so bad. Like, it's because I'm writing on a tablet. Yes, I will blame it on the tablet. And then I'll just do this, shrink it a little. Alright, and then do that. And then I'll just really shrink it. What happened to it? Oh, okay. And then I'll just, I don't want to write a paragraph. I mean, she said we didn't have to. I don't know why I'm doing this. Okay, anyway. I performed a one sample T test for the mean difference in distance traveled by gummy bears. I first checked for randomness and determined that there was a simpler what? See, this is why we gotta spell check. Simple random sample of 30 gummy bears. So let me fix that up here too. Alright, I then checked for independence by observing if the sample size n was less than or equal to 10% of the population of all gummy bears, and that held to be true. Finally, I checked for normality by determining if the sample size was greater than or equal to 30, which held true as well. Since all conditions were met, I proceeded with conducting a significance test. Significance test with a significance alpha level of 0.05. For the average difference in distance traveled by gummy bears in respect to each treatment. After performing the calculations, the interval, the t-test, resulted as follows. What was it again? Negative 0.1044. Hence, I then found the probability value of I don't even know. The p-value sounds better. The p-value using the t statistic. With a, I didn't do it with a calculator, but I did do it with a calculator because I set it up using, well, I don't even know, using t.cdf function from ti. Well, I technically did it with, you know, what was I gonna say? I did it with with Python, but it's the same. Hence, because the p-value of p-value of 1.08, what was it again? 1.0824 was greater then the alpha level of 0.05, we fail to reject or is greater than HO and have and do not have convincing evidence that there is a difference in the average difference in distance traveled by gummy bears. Honestly, I'm gonna be so honest, I don't even know if this test makes sense. Like, the wording sounds so bad. But you know what? We're gonna go with it because I wanna be done with this. And I have other things to do, right? Yes, okay. Anyway, I'll fix it one of these days. The math is right though. Let me check the answer. Hypotheses, test, calculator. T. Just to show you. U equal to 0, not equal to 0, and is 30. X bar was negative 0.9 something. What was it again? Negative 0.9. Sigma. Well, we didn't have sigma. Standard deviation, there we go, was 48, blah, blah, blah. And then level of significance 0.05, solve. What the heck? What am I doing again? Students distribution table, area, C, so we got the T right, the negative 0.1044, whatever. P-value approach, blah, blah, blah. Oh, they used the table. Rejection rule. Reject HO if p-value is less than or equal to alpha. P-value 0.40 to what? What the heck? Oh, because they use the table. Is greater than alpha 0.5, so we do not reject HO. That means we fail to reject HO, and we do not have convincing evidence that the mu difference is not equal to 0, meaning that we don't have convincing evidence that there is a difference. Yeah. Anyway, that was that. Was that the C table or the what? Oh, they used T table, student T table. Oh, critical value. Yeah. Anyway, let's just show you that I'm right, or that my code is right at least. So that's it for today. Let me see. Next, I'll do conclusions and reflections, and then one thing I want to fix or look into is this over here. Let me just. Okay, the Gummy Bear Project part is done. Now I'm just gonna do a little bit of exploration on this function because what the heck? Oh, okay. What day is it? Day 3/23, June 6, 2022. Oh, it's Monday. Week 49. Alright, I'm gonna add this code, right? So now, I'll just show you real quick. No, because TCDF is different than CDF. Let me see if, I'm just trying to find, okay, let me think real quick. So, right tail test, right? So let me do Khan Academy. Right tail test. Practice. That's not how you spell practice, but okay. I don't want videos. Whatever. I'll just pick whatever's here. my null hypothesis. I've been calling it my original hypotheses. Whoops. Alright. Hypotheses testing. Essential oils, blah, blah, blah. What? No, not this one. What? I never said that. What? I said see more. Why does it keep doing that? I'm saying see more, not... Oh. Whoops. I just need an example to do to like try out my functions. No. Verizon? What? That's funny. Oh my god, what? That's it? Can I have an actual, like, example, please? No. Here we go. No, I don't want video. Jesus Christ. Oh my god, let's go back. Alright, I'm just gonna go to my Khan Academy and see if I could find an assignment where they had those types of questions, because I want to troubleshoot my function and make sure that it's right. Okay, let me go back here. Learner's home. Alright, past. Next. Alright. Inference, blah blah, test statistic and p-value. Inference, no. Finding critical value, calculating a t-interval, writing hypotheses for a test about a mean conditions, calculating main conclusions. I need to calculate the p-value. Calculating the p-value in a t-test for mean. I'm so tired. Amelia was testing with a sample of 10 observations. With a sample of 10 observations, her test statistic was that as soon as conditions for inference were met. Right, okay, yeah, this is perfect. This is what I needed. Okay, so I need to make sure that this thing is giving me the right answer. So let me go over here. This thing is kidding me, right? Oh my god. Go back again. Alright, calculating t-test. P-value, let's go. Alright, perfect. Alright, so for this one, it says that the mean is, the sample size is 10, so n is 10. The mu is actually 15, and the t-stat is equal to negative 2.77. This, what the heck is going on now? Oops, it's because I did, it's supposed to be t, not t-stat. Alright, is this a two-tailed test? No. 0.109. Okay, just wanted to make sure my function was right, because I was thinking, right, when you use, let's say I use from scipy import stats, and I do stats.norm.cdf, that takes, what does it take in again? It takes my x value, and then it takes my mean, whoops, what the heck? My loc, and my standard deviation, which is my scale. It takes one, let's say 0, normal distribution, and I take, like, let's say, what is it, 0.5? So that's gonna give me 69. What the heck? In a normal distribution, if I do, what does that look like again? Did I go crazy? What am I doing again? Oh no, yeah, that's right. So like like the cumulative distribution up until 0.5. What does that look like again? Let me import numpy. 1 second, bear with me. np.linspace. So let me set up my variables. So my mean is 0. My standard deviation is 1. And so my linspace, I want it to be my mean minus 3 times my, 3 times my standard deviation. And then my endpoint, I want it to be my mean plus 3 times the standard deviation. And then I want like 1,000 values in between. Okay, perfect. And then I'll do, I'll import matplotlib.pyplot as plt, and I'll do plt.plot, and we'll just plot in. Actually, hold on. I had to do stats.norm.ppf, and then put in my, set that equal to my x values. Oops. And then this, take in my x values. And then my loc is mean, my scale is my standard deviation, and that is my y values. So that equals my y values, and then I want to plot my x values on the x-axis and my y values on the y-axis, and that should plot a fairly normal distribution, but it's not doing that, so what the heck. All right, let's think. Probably 1,000 if I do mean, scale, loc. So if I delete this, oh no, go back. This thing is seriously irritating. If I do mean minus 3 times the standard deviation, 3 plus the standard deviation, and then I do 10,000 as my x values, ppf, pdf. There we go. Whoops, sorry, I used ppf instead of pdf. Alright, wait, no, that doesn't make sense, because pdf, yeah, never mind, yeah. Okay, anyway, see, this is what it looks like, what a normal distribution looks like. Well, this is actually a standard normal distribution because it has a mean of 0 and a standard deviation of 1. And basically, what I'm trying to figure out, we can use this, right? So this is just a graphical representation of what I want. Let's say this represents, no, but then that's for proportions, not probability. Let's say I'll do plt.xlabel, and this is like student, or just like, let's say like grades. And then I say like, what proportion of students, or like student grades, what proportion of students got a 1 or higher? 84% of the students got a 1 or higher. Does that make sense? If I have, right, because this is supposed to be mean, and this is supposed to be the STD. What if I changed it so that the mean was actually, let's say the mean was like an 80, right? And that each point deviated, like, let's say 4 points from the mean. And we didn't have 1,000. Actually, let's keep it as 1,000. Right? And then let me run that again. It's gonna look the same, but here it should change, right? Exactly. So that's the proportion of students who got a 1. Makes sense. But if I say what's the proportion of students who got an 80, it should be close to the mean, right? Because 50%, the mean is the middle. Well, the mean is the median, actually. Interesting. 50%, right? Because the mean is the average, right? So what if I said, interesting. What about an 89? 98%. Oh, because it's a cumulative. Right, that's the, oh my god, those are all of the students who got up until 89. Because this takes, like, negative 1e99 up until 89. Oh, that makes sense, right? And because, oh, yeah, that makes sense, right? Because the middle is 80, right? So if I do, okay, what's the proportion of students who got up until an 80, right? Who got below an 80, which is what stats.norm.cdf is going to give me. It's going to be 50% because that's in the middle, right? It's like halfway, right? Okay, that makes sense. But then here's the thing. My thinking was, because of that, like, CDF runs on just calculating the proportion of a certain x value, in this case 80, if only like below or like before it, right? And so over here, it just didn't make sense to me that if I said that t was like less than 0, then the p-value would be equal to 1 minus area. Why would it be less than, I forgot why I did this. If type test is equal to no, is it always when t is less than 0, it's a left-tailed test? And when t is greater than 0, it's a right-tailed test? That's weird. I don't think that's right. But then I did get the answer right, so what the heck? It's 0.010. Right, because if I have 0, what's the area? Let me return the area also. I want to be able to return the area over here. So print area. That's the area, right? So that's the area, and we get that, right, by just doing stats.t.sf. But SF actually takes the opposite of CDF. SF is actually 1 minus CDF. Interesting. So is this the equivalent of a t-test and not a t-CDF? Interesting. I'm trying to think here. Let me think. So if the type test is a two-tailed test, p-value area times 2, which makes sense, right? But then if the type test is a no, and if the t is less than 0, but is that the, oh, that is t. Wait, then what the, this gives the area. Then why did I use stats.t? Oh my god. Oh, I think I understand why I did that, because if this is the opposite, then I had to do the opposite here. So maybe I could rewrite the function so that it's, hold on. Maybe I can rewrite the function. Hold on. I'll have this here, and then instead of doing SF, I'll do CDF. And then of doing that, I'll do if it's greater than here, and then less than here. Run that, say no. It should give me the right answer. Oh my god! Stop! See, I knew it. Look at me. Oh my god. Literally, I'm so proud of this. Oh my god. I am so proud of this realization. Okay. Yeah, so I was wondering, right? Because over here, I noticed that I used SF. Or the whole thing was that I thought that this looked a little bit of opposite, right? Because generally, let me make, I have to always use my whiteboard. Pretty whiteboard. Let me pull it to the side. All right, so the idea is that whenever you're using CDF, which is a cumulative distribution, or sorry, density function, not distribution function, you want to be able to, what the heck did I just do? All right, so CDF, if you have a normal distribution, right? So what CDF does, oh, you know what, let me just save the image. All right, paste that in there. Wait, lock, not paste. Okay. So let's say for student grades, right? Let's say that this is a normal distribution for student grades. It just shows the grades of students, whatever. Let's say I want to figure out the proportion of students who got an 80 or lower. So I would do, right, in my calculator, I would actually do second norm 2. Second norm, no, not second norm, second stats 2. Second something, I forgot, whatever. Either way, you get to the CDF function, norm CDF, which is the same thing as just stats.norm CDF over here, and then it asks you for a lower bound, upper bound, and then what else does it ask you for? Lower, upper, mean, mu, and sigma. All right, so if I want to say, okay, what proportion of students scored less than an 80? So 80 is right here. We know that 80 is our mean. And so the area that we're trying to find is this here. Like that area right here represents the proportion of students who scored less than an 80. And so it would make sense, right, that when I did the same thing in Python, I did stats.norm.cdf 80 and I made it like log, mean, scale, which is standard deviation. It gave me 50, right? Because it's 50%. Like this is 50%. It's half of it. So it made sense that that's the proportion of students who got less than an 80. Now, here's the thing. What if I wanted to find the proportion of students who got greater than an 85? So in that point, 85 would be, why can't I draw a straight line? 85 would be right here. And so the area I'm trying to find is this area right here in red. Whoa, what the heck? Right? This area right here. Okay, that's just so ugly. Sorry, come on, you could do better. Okay, we're gonna leave it as that. So this area in red represents the proportion of students who scored greater than an 85, right? Now, here's the thing though. Oh, by the way, I didn't explain how to do it in the calculator. So if you have a TI-83 or TI-84, lower bound would end up, for 80 would actually be negative 1E99, upper bound would be 80, and then the mean would be whatever the mean was, which was 0, and then 1. And then it would give you, 0.5. The reason it's negative 1E99 is because normal distribution goes to negative infinity, right? And so we don't have that in our calculator, so we do negative 1E99. But in Python, right, the principle is that in Python, CDF actually calculates the probability of, not the probability, excuse me, the proportion of a certain point, but only below or to the left of it. Like it never does higher. So it's a problem when we want to calculate like the proportion of students who got greater than an 85, because CDF doesn't do that. It only calculates the proportion of students who got less than 85. But if you could just use your logical thinking, if CDF only calculates the proportion of students who are left than 85, then to get this area right here, all you have to do is 1 minus whatever proportion of students that's less than 85, right? So we'll do that, right? So that was the principal idea. But like in TI, I'm like going all over the place. In TI 83, your calculator, and TI 84 also, you have to, specify the interval in which you are calculating. Because actually, let me say, hold on. No, yeah. So here's the thing with Python, your calculator versus Python. So Python CDF function only calculates like before or below a certain point. And then in your calculator, it actually gives you the exact probability that you want because you're specifying the interval in which you want the area to be calculated. Because you're saying like -1e99, you're saying, okay, I want from -1e99 all the way to 80, it's going to calculate that that area under that curve. But let's say I want greater than 85, I'm going to do norm CDF. My lower bound would be 85, then +1e99, and then 0 and 1, and then that's the same thing, right? So you're saying I want to start at 85, I want to go to infinity with a mean of 0 and a standard deviation of 1, and because you're specifying that interval, it's going to calculate this interval right here, right? And so because of that, in your calculator, you don't have to do 1 minus anything. It's going to give you the area that you are asking for, only because you're specifying your lower bound and upper bound. But in Python, you can't specify your bounds. There's no interval. The only parameter that it takes is the x value that you want to find the proportion above or below. And so because of that, you would have to use your own logical thinking and say, okay, you know that in Python CDF only calculates the proportion below, right? Below or before a point. So if I'm going to calculate, if I want the proportion of students who got an 85 or greater, right, as a grade, then in Python, what I'm actually calculating with stats.norm.cdf 8501, so this is the mean standard deviation, that's going to give me this green area. So in order to get what I want, let me change it to 85. It's going to give me, 89%? So that's 89% of the students got lower than an 85. So what do I have to do in order to get this red part? Well, in order to get the red part, right? In order to get the red part, the red part is equal to 1 minus, right, the green, right, that 89%, or that 0.89. And when we do 1 minus that whole thing, right, we get, what do we get, 10%, 10%, which makes sense. 89 plus 10, 99, which is almost to 100. But if you actually add up the numbers here, let's do this number, and then take whatever this number is, it's going to give you 100%. Or 1, right? So 1, right? So that's what it is. So that's how you get that. But in Python, there is another way. Instead of doing 1 minus CDF all the time, there's a function called SF, right? And so again, if I do 1 minus blah, 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 I could do the same thing by just taking this, right? And taking this, and then instead of using CDF, I use SF, and it's going to give me the exact same answer. Because this function, SF, is the same thing as 1 minus CDF. So instead of doing 1 minus CDF all the time, just use SF. And so that's what I realized over here. I was like, why does this look a little opposite? Because it doesn't make sense that if t is less than 0, then it should be like a left-tailed test. Because wait, hold on. Now I'm confused. Wait. So if t is less than 0, then it's a left-tailed test, but that didn't make sense to me because if it depends on if t is greater than 0, the p-value is equal to the area. Oh, here's what didn't make sense to me. So I did 1 minus the area if t is less than or equal to 0. But that didn't make sense because 1 minus the area would give you the red, right? It would give you the red part. because in CDF, if you're using CDF, it's gonna give you the green part, right? And so if t is less than, right, because again, less than is below or before an x value. So in this case, pretend it's x. Like, let's say x is less than 0, whatever that point is. Then if it's below or before, again, it's you can use CDF and you don't have to do 1 minus anything in Python. Not your calculator. Your calculator is like another, it's like you put your interval, you get what you get. But in Python, right, you use CDF, that is if it's less than, right, a certain point, because it's going to give you just that area. So it didn't make sense that the p-value would be equal to 1 minus that area until I saw that instead of CDF, I used SF, which is the same thing as 1 minus CDF, and so it's essentially the opposite. So here, because I use CDF, and now it makes sense that if t is greater than 0, right, then the p-value would be 1 minus that area, because that t, which is, you could think of as your x point, that it takes in over here, like this x point, you can think of it as it taking the red part, 1 minus the green, right, is equal to the red, so the p-value. So red is equal to 1 minus green. And then it would make sense that if t is less than, right, so that's when you would use your regular CDF function, then that would just end up being the area, right, because that's what you used here at the beginning, right, just the area, because it calculates the CDF, it calculates the proportion below or before, which is what the condition states, that if t is less than 0, so then it's just p-value equals the area. So this makes more sense to me. So I was like, why does this make sense? And it's because I used SF instead. So, oh my god, we love this right now. We love this. Okay, anyway, yeah, that was a little of my rant. I was just trying to figure out, because it didn't make sense to me, and I was like, oh, yeah, but anyway, it's still right, and because we're in the mood here, why don't we just start doing some problems to just make sure we're right. Whoops, never mind. Oh, actually, this is perfect. Hold on, this is the function that I was using the other day. So, I told this the other day in day 321 that I made all these functions because I didn't have time to do the Khan Academy homework, and so I had the functions I just put in whatever it said in the problem into my functions, and it would give me the answer. I even went as far as to write a function that would give me exactly this, right? Like this one is the one by parts. So I would do basically, I'll paste this one in, right? And so my n says what, 5 observations, so I would change my n. I'm just going to do it myself. So I'll do my n to 5. My x bar would be my mean, and so that would be 40, right? And then my standard deviation, they would usually say it 3, right? And then my mu is whatever number's here, which is 45, and then I would just literally run it, and it would give me the thing by parts. So 40 minus 45, 3 over the square root of 5. Ooh, with how many? Ooh, this one is a new one. With how many degrees of freedom? Well, that would just be, what's n minus 1? What's n again? Sample of 5, 4, with 4 degrees of freedom, right? And t is, oh, but this one is actually different. This one only gives you the equation. T is greater than 40 minus 45, 3 over square root of 5. T is greater than p-value. What does t is greater than mean? Which of the following represents the p-value for Jamarion's test? Oh, I'll just put it in this function then. Whoa, what did I do? Oh. Oh, baby, baby, how was I supposed to know that something wasn't right? And I'll actually, you know what? I'll take the t function too, so that I could actually have that. So what was it again? 5. It's in the same thing, right? Okay, so what's my t? My t is this number right here. So I'll take that and I'll make sure to input it there. And then my n is 5. My mu was 45. So I run that and it should give me my p-value. Is this a two-tailed test? No. My p-value is 0.0102. So what does a t greater than mean though? It's either this one or this one. 40 minus 45t is greater than... Oh, does it mean what this is? Why am I screaming? Literally, I'm so sorry. This is the area, right? And then it'd be the same thing. So it just stayed the same. So that means that it's less than. Let's check. Oh yeah, okay. Right. So I haven't written a function I think for this specific one, but I just used logic reasoning in my function. So basically, it said t is less than 40, whatever. So how did I choose between the first one and the oh, it's because the hypotheses used a less than symbol. Okay, that makes sense. But also the fact that it actually literally is less than. I was like, okay, it's less than, so because the area stayed the same, so I was like, oh, so then t must be less than. So I was like, okay, less than. Anyway, that's one. Anyway, yeah, let's just stop here. Okay. Maybe I should put the link. Oh wait, I don't have it. I just exited out. Was it this one? Alright, so put that there. Why did it put it as a heading? Someone tell me. Khan Academy. That's not how you spell Khan Academy, Sarai. Alright. So beautiful. And yeah, that's it for today. Honestly, I kind of want to save this. Where's my stats? Where's my stat stuff? I thought I had a stat folder. No, not there. Oh, here we go. Alright, close that out. Done with that, closing it out, close this one out, and do we have anything else to do? I think that's it. Alright, bye.